Hello everyone. Hope you all are doing well, taking care of yourself as well as your family. Uh, in the previous video lecture, we have discussed the uh, main components of Pelton wheel turbine, also drawing of velocity at the inlet and at the outlet of Pelton wheel turbine, and various efficiencies. In this lecture, we are going to discuss some design aspects which are generally considered while designing the Pelton wheel turbine and numerical based on it. So let's start. So starting from the design aspects of the Pelton wheel turbine. So first design aspect is the velocity of jet, which can be calculated by using equation V1 is equal to CV under root of twice of GH, where CV is the coefficient of velocity and the value of coefficient of velocity is ranges in between 0.98 to 0.99, and where H is the net head. Next, mean diameter of the wheel, which is also which is also called as pitch diameter of pitch circle. In the previous lecture, we have discussed pitch circle. What was the pitch circle? If we consider the center of the bucket, and if you draw the circle from all those every bucket center point, starting from the center of the runner, then that circle is known as pitch circle. So whatever diameter of the pitch circle can be calculated by using this equation, which is given by u1 is equal to u1 is equal to u2 is equal to pi dn upon 60, where this d is the diameter of wheel and this n is the speed of runner in revolution per minute. We have also discussed in the previous lecture this u1 is equal to u, both are same because both the points at the outlet and inlet and outlet point of the bucket from where we have drawn the cross section and we are considering inlet point and outlet point of the jet, both are located at the same radial distance from the center. That's why those u1 and u2 both are the same. Next one is the velocity of wheel. If the velocity of wheel u is not given, then first compute velocity of wheel by using this relationship u is equal to ku under root of twice of gh, where this ku is the speed ratio, which can be calculated as velocity of wheel upon velocity of jet, small u upon v1. Its value generally ranges in between 0.43 to 0.4548, and most commonly its value is taken as 0.45. The next component is area of jet. So area of jet can be calculated as small a is equal to q upon v1, where q is the discharge flowing through the runner and v1 is the velocity of jet. If this q is not given, then compute that q from the overall efficiency or equation of power. Next design aspect is the angle of deflection, which varies in between 160 to 170 degree and can be calculated as 180 degree minus phi, where phi is the outlet tip angle and which is varies in between 10 to 20 degree, and most commonly for the angle of deflection value is taken as 165 degree. If it is not given, then one can assume this value. Next, jet ratio, which is denoted by the m. It is the ratio of pitch diameter of the wheel to the jet diameter, which is given by m is equal to capital D, diameter of the wheel, divided by small d, which is diameter of the jet. The value of jet ratio is varies in between 11 to 14, and in design it can be taken as m is equal to 12. Next, number of buckets on the runner. The number of buckets on the runner can be calculated by using this equation: z is equal to 15 plus 0.5 m, where this m is the jet ratio, or z is equal to 15 plus 0.5 capital D upon small d. This capital D upon small d is the jet ratio. Next one, number of jets. So number of jets can be calculated as by dividing total discharge with the discharge flowing through one jet. And the last one, length of bucket or height of bucket can be computed as by taking value in between 2.4d to 3.2d, where d is the diameter of the jet. Next, width of the bucket. Again, It can be considered in between 4D to 5D. Again, next, depth of the bucket, it can be considered in between 1.2D to 1.9D. And next one is the angle phi, which is the uh, outlet tip angle, which is in between, can be taken in between 10 to 20 degree, and angle beta, which is angle made by the jet at the outlet, is 5 degree to 8 degree. So remember those points. Again, we will summarize our previous video lecture here. So what we have discussed in the previous video lecture, work done per second in case of Pelton wheel turbine is given by the equation rho a v1 multiplied by v1 vw1 plus minus vw2 multiplied by u, where this plus sign will be taken, uh, this plus sign will be taken whenever our beta is less than 90 degree, and this negative sign will be taken whenever my beta is greater than 90 degree. And if my beta is equal to 90 degree, in that case put vw2 is equal to 0. This is also known as power equation. Next one is the hydraulic efficiency, which can be computed by either by this equation vw1 plus minus vw2 multiplied by u divided by gh, or twice of vw1 plus minus vw2 multiplied by u divided by v1 square. Again, overall efficiency is given by shaft power P divided by water power, that is given by rho g qh. Again, we have discussed some thumb rules in the previous video lecture. So remember those. If efficiency is given, consider it as hydraulic efficiency. If Q is not given, calculate by it using overall efficiency equation or power equation. If U is not given, then calculate it as by using U is equal to KU under root of twice of GH, and then use this equation to compute value of D. And the last one, once calculate number of jet and round it to the next full integer, then recalculate diameter of jet for the modified discharge. So let's start our first numerical. So in the first numerical, it is given as Pelton wheel. It is to be designed for the following specification: power brake power at the shaft, which is also shaft power or braking horsepower, is given as 9560 kilowatt. Head at the turbine, that is 350 meters. Speed as the 750 revolution per minute. Overall efficiency is given as 0.85%, and jet diameter, which should not exceed the 1/6 of the diameter of wheel. By using this given data, determine the wheel diameter of the Pelton wheel, diameter of the jet, and the number of jets required. Take the value of CV is equal to 0.985 and speed ratio is equal to 0.45. So let's sum up all given data. So what we have given: shaft power, head. As remember that here they are mentioned head only. So whenever they are mentioning in the numerical head only, treat that head as a net head, because if it is a gross head, it would be the mention in the numerical, or it would be the mention what is the head loss or what is the coefficient of friction, but here nothing is mentioned, so treat this H as a net head. Next one, speed is given, overall efficiency 0.85, a ratio of jet diameter to the wheel, small d upon capital D, is 1/6, and coefficient of velocity is given CV 0.985, and speed ratio is given KU. Now whenever in the numerical it is mentioned CV and KU, the first and foremost thing, you should calculate V1 and U, that you can calculate by using CV and KU. So we are going to calculate first V1, which is given by CV under root of twice of GH. So here H is given, CV is given, you can compute V1 is equal to 81.62 meter per second. Next, calculate U, which is given by the equation KU multiplied by under root of twice of GH. So here it is, my value of U is 37.3. Now the first thing they asked to calculate the wheel diameter D. So we know that wheel diameter can be calculated by using relationship U is equal to pi dn upon 60. Just put the value of U and n here, you will get the value of D. Here is my D, which is coming out as 0.95 meter. The next thing they asked to calculate diameter of the jet. We know that diameter of the jet should not exceed the which is given in the numerical, should not exceed the 1/6 of the diameter of the wheel. So just put the value of D here, you will get the diameter of jet, 0.158 meter. Next thing they asked to calculate number of jets required. So number of jets required, we know that, which is given by total discharge from the turbine divided by discharge flowing from one jet. So here we have calculated diameter of jet, and we can calculate the volume of water flowing through this diameter of jet by using velocity and the area of jet, which would be given by pi by 4 and d square. Pi by 4 d square. We can easily compute the volume of water flowing through the single jet and just divide this volume of water, just divide this total discharge with the volume of water flowing through the one jet, you will get the number of jet. So we will calculate one by one. So we will first calculate discharge flowing through one jet. So discharge flowing from one jet will be equal to small q is equal to area of jet multiplied by velocity of jet. So area of jet will be equal to pi by 4 d square. Here d is the diameter of jet, which is given by 0.158, multiplied by velocity of jet, that is 81.62. So volume of water flowing through single jet is 1.6 meter cube per second. Now next calculate the total discharge flowing from the turbine. So we know that for calculation of total discharge flowing from the turbine, we are going to use the overall efficiency equation, which is given by overall efficiency is equal to shaft power upon water power. So shaft power already given in the equation, and just put the value of water power here, rho GQH. So here it is, water power is given by rho GQH. So I can calculate here value of Q by putting the value of overall efficiency that is given in the numerical 0.85. So here I am getting the value of Q is equal to 3.27 meter cube per second. Now put the value here, 3.27 divided by 1.6, you will get the value of value for the number of jets required. So here it is, 3.27 divided by 1.6, the value is coming out as 2 jets. So I just rounded it to 2 jets. It is actually less than 2 jets. So here, as I am rounding off it to the next integer, it's important to recalculate your diameter of jet again. So in that case, just divide this whole discharge Q with the number of jet 2. This will gives you the discharge of water flowing through the single jet, and then compute the diameter D again. So here I have not calculated, that you should do it. Let's move to the next numerical. So our next numerical is given as the Pelton wheel is receiving the water from the penstock with a gross head. So here it is mentioning gross head of 510 meter. 1/3 of the gross head is lost in the friction and the penstock. The rate of flow through the nozzle fitted at the end of penstock is 2.2 meter cube per second. The angle of deflection of jet is 165 degree. Now determine the power given by the water to the runner and hydraulic efficiency of the Pelton wheel. So this is what data they have given. So here they have mentioned gross head, and from the gross head 510 meter, 1/3 of the gross head is getting lost in the friction. So we need to calculate here net head. First thing, the rate of flow through the nozzle is given as 2.2 meter cube per second. Again, angle of deflection is given 165 degree, and we need to calculate power given by the water to the runner, that is nothing but our work done per second equation we are going to use here, and hydraulic efficiency, which is given by P upon rho G QH. So let's sum up again. Sorry, some numerical was remaining. CV is given as 1.0 and speed ratio is given as 0.45. So let's sum up what they have given. Given data, gross head, again head lost in the friction. So 1/3 head is going to lost in the friction. So 510 divided by 3, almost 170 meter head is going to be lost in the friction through the penstock. So I am going to calculate here net head, which will be given by the gross head minus head loss. So it is coming out as 340 meter. And again they have given discharge and angle of deflection as 165 degree. Now while solving those numerical, so in the previous case we have solved it directly, but in this case we are going to sum up what we need to calculate. Once you sum up it, once you write those formulas, you will get what you need to calculate and what you require. So first we will sum up what we need to calculate. We need to calculate the power, that is here they ask power given by the water to the runner. So we know that we can calculate this power by using this equation, rho a v1 multiplied by vw1 plus minus vw2 multiplied by u. Now here if we consider this, beta is less than 90 degrees, so here the sign will come out as a plus. Again, what we need to calculate, what are the unknowns, just sum it up, what we need to find out in those values. So first we need to find out v1, second we need to find vw1, and we need to find vw2. So let's see from where we can find v1. V1 you can calculate by using this relationship cv under root of twice of gh. Again, you can find out by using this relationship because they have given ku, so you can calculate u is equal to ku under root of twice of gh. Now we know that in case of Pelton wheel turbine, vw1 is equal to v1 and vw2. Now we can calculate this vw2 by using outlet velocity triangle by considering angle phi. And next they asked to calculate hydraulic efficiency, which is given by the runner power upon water power. So we are going to calculate runner power here and just dividing it with the water power, rho g qh. So q already they have given. So let's proceed to calculate. So for the understanding, I have drawn the outlet and inlet velocity triangles here. So first thing, they have given angle of deflection as 165 degrees, so I can easily calculate my angle of phi, that is 180 minus 165 degrees. So this angle is coming out as 15 degrees. CV is given 1.0 and KU is given as 0.45. So first thing we are going to find out the V1, VW1, VW2 and U. So let's start from the V1 as they have given CV and speed ratio. So first and foremost thing, you are going to calculate the value of V1 and value of U. So here it is V1 is equal to CV under root of twice of GH. So value of V1 is coming out as 81.67 and U. So value of U is equal to KU multiplied by under root of twice of GH, which is coming out as 36.75. Now the next thing, we are going to calculate the other parameter what we require here, VW1. So from the inlet velocity triangle, my VW1 will be equal to the VW2. So my VW1 is 81.67. Now we need to find this VW2. So while calculating the VW2, we are going to use this angle phi. So cos of phi will be equal to this adjacent divided by hypotenuse. So my cos of phi would be equal to u2 plus vw2 divided by vr2. So while calculating this vw2, we already know phi, we already know u2, but we need to find the vr2. Now in case of Pelton wheel turbine, we know that vr1 is equal to vr2. So here I am going to find the vr1, which would be given by the equation v1 minus u, that would be equal to 44.92. So let's proceed to calculate. Once I find out the VR1, now consider the outlet velocity triangle. Consider the outlet velocity triangle cos of phi. So cos of phi would be equal to u2 plus vw2 divided by vr2. So I can write down this equation as vr2 cos of phi u2 plus vw2. Now we know that u2 is equal to u1 is equal to u. So I am rewriting it as vr2 cos of phi is equal to u plus vw2. Now we can calculate here vw2 is equal to vr2 cos of phi minus u. Now we know that in case of Pelton wheel turbine, if I am ignoring the frictional losses taking place at the bucket, at the vane, so we can calculate, we can consider vr2 is equal to vr1, which we have already calculated, 44.92 meter per second. So here I am just going to put the value 44.92 meter per second multiplied by cos of 15 degree minus 36.75. So my value of VW2 is coming out at 6.64 meter per second. Now I can easily compute my work done per second, which is given by the equation work done per second is equal to rho a v1 multiplied by vw1 plus vw2 multiplied by u. So here a multiplied by v1, I am going to replace it with the q because they haven't mentioned diameter of the jet and they have directly given q to me. So I can, instead of going to calculate the area and all, I am just directly putting a multiplied by v1 as q. So my work done per equation will get modified slightly here, and I am going to put the values of all the parameter in this equation. So I can get the work done per second or power given to the turbine as 7139.8 kilowatt. So this is my power given to the runner. Now next thing, they asked to calculate the overall efficiency. Now we know that overall efficiency is given by the equation runner power divided by water power. So this runner power we have just calculated here. Whatever our runner power, here it is runner power, and water power we can calculate by using this equation rho g q h. We already know the value of q and h, so just put those value. Rho and g already is a constant, so just put the values here. You will get the value of efficiency, hydraulic efficiency, which would be given by 97.3%. So those numericals are very simple. Just remember the procedure, or just sum up what you need to calculate first. So if you see here, first thing we have summed up what we need to calculate and what we need to find, and then we have calculated all those required parameters, and then we have easily solved the numerical. So here I have just previously sum up. We need to calculate the power. For the power, what are the unknowns, how to find those unknowns, and then proceeding for the hydraulic efficiency. Now let's move to the next numerical. So this numerical is based on the design, last numerical. So in this numerical they asked to design the Pelton wheel turbine. So a Pelton wheel turbine, it is to be designed for head of 60 meter, which is running at the speed of 200 revolution per minute. The Pelton wheel turbine develops 95.64 kilowatt shaft power. So they have given the power. The velocity of bucket is 0.45 times the velocity of jet, and overall efficiency is 0.85%, 0.85, sorry, and CV is given as 0.98. So for this given data, we need to design the Pelton wheel turbine. So design of Pelton wheel turbine includes the diameter of jet, diameter of wheel, and width and depth of bucket, and number of buckets. So those we have already discussed. So let's first sum up what they have given. The first thing, they have given the discharge, head, and second thing, they have given the speed. Again they have given the shaft power, which is developed by the turbine under the head of 60 meter, and again they have given the velocity of bucket is 0.45 times the velocity of the jet. So here I have written the equation for it. U is equal to 0.45 V1, and again they have given overall efficiency as 85%, 0.85, and CV they have given as 0.98. So first thing, we are going to, first and foremost thing, always be, as CV is given, we are going to find the value of velocity of the jet V1. So always remember, first and foremost thing, if CV and KU is given, first calculate V1. So here we are going to calculate first V1. CV is equal V1 is equal to CV under root of twice of GH, and just put the values. 0.98 under root of twice of 9.81 multiplied by 60 is equal to, V1 is coming out as 33.62. Now first thing, we are going to calculate the diameter of jet. So diameter of jet, we know that it's given by Q is equal to area multiplied by velocity, where A is the area of jet and V1 is the velocity of jet, and Q is the discharge coming out or water flowing through that jet. So calculate this Q, because they haven't mentioned Q, and we also need to calculate the diameter. So if you remember our first numerical, in that we have calculated diameter first, and then we have calculated the number of jets. But here we are going to design the single jet, because here they haven't given the diameter of jet as well as they haven't given the Q. So we are going to calculate design the single jet. So for that single jet, just first find out the Q, and we are going to assume that whole water is flowing through a single jet. So here calculate Q by using overall efficiency equation, which is given by P shaft power upon water power rho g QH. Just put the value of all the respective variables. So just calculate this Q. So what you are getting here, Q is equal to 0.191 meter cube per second. Now just find the value of area, and just put the value of area as pi by 4 d square. So your diameter is coming out as 0.085 meter or 0.85 mm. So first we have calculated diameter of jet. Now second thing, as we have calculated already V1, we can easily calculate U, as they have given U is equal to 0.45 of V1. 0.45 times the velocity of the jet. So I am going to calculate u, which is coming out as 15.129 meter per second. Now second thing, they asked to calculate diameter of the wheel. So I can calculate your diameter of the wheel, as I told you previously, while designing the Pelton wheel turbine or calculating the diameter of wheel. Use the relationship of u is equal to pi dn upon 60. Just put the values of u and n here. You will get the value of d. So diameter of wheel is coming out as 1.44 meter. Now last thing, they asked to design Pelton wheel turbine, so we need to design the all dimensions of the bucket. So first thing, width of bucket, you can take 4 to 5d width of bucket, so which is coming out width of bucket as, here I am assuming that 5 multiplied by diameter of jet, it is 425 mm. The next one, depth of bucket, so you can take the value of depth of bucket in between 1.2 to 1.9 d. So here I am taking 1.2 d, it is coming out as 102 mm. The next one, number of bucket, so number of bucket is given by 15 plus d, half of capital D upon small d, where capital D is the diameter of it and small d is the diameter of jet. Just put the values. Number of bucket is coming out as 23.47. Round it for the next integer. So here number of buckets are 24. So this is the numerical which are based on the design aspects of the Pelton wheel turbine. So go through some other other numericals and make the practice of it, so you would not get any difficulty while solving those numericals. Just remember those thumb rules while designing the Pelton wheel turbine or consideration. Just like say CV, if CV is given, then calculate first V1. Again, if KU is given or anything relation is given related to U, just calculate this U by using equation U is equal to Ku upon under Ku multiplied by under root of twice of Gs. So remember those two formulas, because first and foremost thing you are going to do this, and thereafter you are going to find the other parameters, like say diameter is asked, then use the relationship is equal to, U is equal to pi dn upon 60 likewise. Or you can also do one thing, just sum up what they asked to calculate. Once you summed it off, it is easy to find all the variable, all the necessary variables which they asked to calculate. So here in the previous case we have summed it up. What we need to calculate, power and hydraulic efficiency. So power can be calculated by using equation this, and then just we have highlighted what we need to find while calculating the power, and just we have calculated those variables by using whatever the relations we have, or whatever the relation we have from the inlet and outlet velocity triangles. So numericals are very easy on the base on the Pelton wheel turbine. So go through some numericals and do some more practice. This is okay, do some practice. Thank you.